All right, so let's see. Let me find the questions here again. Okay, so here's right. Oh yeah, 58 here. Yeah, this is a really good one.
Yeah.
I
think in a previous session, somebody had asked like for a specific letter off of it, but
yeah,
maybe just seeing through the whole thing work through would be a good way to go.
Okay. Yeah, let me do this. Let's see. Okay, so chapter 33, number 58, page 1. Okay. And so kind of the first thing is make sure you understand it was actually a conversation that you asked, I think, in session 1, because you asked me when we had that inductor, how do I know that all the current goes through the inductor? And I'm going to say, keep that in mind, because the first important and critical piece is to notice that when this problem gets started here, that switch number 1 and switch number 2 are closed. In fact, as I'm drawing the picture, maybe I should turn on my phone here. And connect the outputs here, screen share, phone, got it. And the big piece to see at the beginning Oops, hope I didn't do any damage there. Trying to connect and I turned it off while it was connected. Let me try that again. All right. So the big thing to realize, so I'll say it again, we were talking about this in the first session, is to realize that if you ever have a situation where one particular path has zero resistance, it means there'd be zero voltage.
Right.
The other particular path must have zero voltage. And the best way to answer that is, well, with no current going through there. So when this one gets started here, it says in A, let's see. In the circuit shown, assume that all the parameters except for C are given. Now, I'll even add the reason that's relevant is because this problem doesn't give us any numbers. And so when you give an answer, what symbols should you use? And the general rule is you always use the symbols that were given in the problem. So in our case, it would be omega, maximum voltage, the resistance, and the inductor, but not C. Okay, so none of my answers should have a C in it. So I should readjust it if it, if I think I'm done and I see a C in it, I should figure out how to solve for that C. And you see that here when it says here in A, find the current as a function of time. So the current as a function of time would be the voltage as a function of time. Or maybe I should say the more general case when we have an RLC circuit is that it's the maximum voltage divided by the impedance times whatever phase or function it has, which this time it's a cosine. Sometimes they give me sine function, sometimes they give me cosine. That's just a matter of where you want to call time equals to 0. Then you have a omega t, and then there is some phase that is created because of your inductors and capacitors. So I'll begin by saying that's kind of the general solution that was worked out with an LRC circuit in series. So keep that in mind. And then, as you were asking at the, I guess it was right before the break, but I'll also say that, you know, I'll put together a video for you, number, what was it, 65. There's a really nice way of solving a bunch of trig functions that are out of phase with each other, and it's called phasors. But when your author does that, he says then you can get the answer to these two pieces. That is the impedance, which is a combination of everything that is opposing the current. The resistance, the reactance of the inductor, and the reactance of the capacitor is given by this square root of R squared. And then the difference between the reactance of the inductor and the capacitor. And in the phasor diagram, those are squared, so you use Pythagorean theorem to get the total impedance. And then the phase is determined with a little trig function, but it depends on the effect of the inductor and the capacitance reactance compared to the resistance. So that was the general solution, discussion about what do you get when you have an AC circuit and you have the three of them in series. So I'm going to just take those ideas and apply it to this equation over and over again, depending on what parameters they say are significant. See, like the first one here, it says, A, find the current as a function of time. Now, that's why I was pointing out a moment ago, when these switches are closed, all the current goes around the inductor and around the capacitor. It's as if we don't even have an inductor and a capacitor in the circuit.
So the only thing we start with is the resistor.
Right, right. So that would tell me that the current as a function of time. And this first step here would be the maximum voltage. And then as I look at the impedance, well, the XL and the XC are nothing. I mean, they're zero. It's not even there. And so all I have is just really a resistor. And so my impedance really is just the resistance. And then when I write out cosine of omega t, I can see right away that the numerator would be zero. So the phase angle would be zero. And so I would just kind of quickly write down, this would be the current as a function of time. There's only a resistor, so I divide by the resistance, that's just Ohm's law, and then there is no phase, because you get a phase either leading or lagging depending on the inductor and the capacitor and the relative size of the two.
Okay.
So that makes A pretty easy. I think it also makes B pretty easy because it says find the power delivered. And so the power is the RMS, or I should say the average power. Does the question say average power? I'll find the power delivered to the circuit. They don't say.
It doesn't say average.
Average. So maybe I'll do both. I think I remember working on this before with somebody, and the answer gave average power. So I'll put I squared R for average power, but then I'll do instantaneous too in here in a second. The RMS is the maximum current divided by the square root of 2. Of course, RMS is kind of the nice thing because RMS gives you the average power. That's why we invented the phrase RMS. But we call it RMS because what it is that you take the square, then you take the mean of it, and then you take the square root of that. And it turns out if you do that for sinusoidal shapes, you can divide it by the square root of 2, the maximum.
Okay.
Okay, and so that was kind of another little derivation thing we did. So this would say then that it's I maximum squared over 2 times R. Now, as I was saying earlier, you should probably always finish a problem in the parameters they gave us. So the maximum is actually this thing up here. So let me leave the 1/2 alone and write this as I maximum squared over R squared. squared and then times R. One of the R's will cancel off, and you'll get V maximum squared over 2R. And that's probably the answer they are looking for, because it's in terms of the givens, the maximum voltage and the resistance. But I should continue on and say, make that same comment that I'm not certain that the author is asking for average power, because he didn't say average power. So it might be nice maybe to take this one step further and say, all right, so the instantaneous power, so I'll say power as a function of time, would simply be the voltage as a function of time multiplied by the current as a function of time. Now, the voltage as a function of time is that V max cosine omega t. And the current as a function of time is what we did in A. So that would be V max over R times cosine omega t. So if the author was looking for the power at one instant, it would be V max squared over R and then cosine squared omega t. And I suspect, though, and you can see it now, that if they're asking for average power, since a cosine squared looks something like this, it goes up and down and up and down and up and down, it averages 1/2. So the average power, I could just replace this with 1/2, and I would get V max squared over 2R, which of course is the same thing I got a moment earlier when I said, why don't we just calculate the average power?
Okay.
And brings me to a curious question myself. This is what, chapter 33? Let me scroll down here to 58 and see if they're looking for average power or instantaneous, but I'm pretty sure working this out. Let's see, currents, yeah, that matched. Yeah, and then they just gave this, so they didn't give the cosine squared. So they're not asking for the power at one instant, but averaged over a period of time.
Okay. But it's still good to know that too.
Yeah. Okay. Now I think the problem gets a little bit harder here in C, because in C, what does it say? Let's straighten this out. C says, find the current as a function of time after only switch 1 is open. Well, let me come back to our beginning discussion, because now if switch 1 is open, I have an inductor. So I got to include this piece to the puzzle, the reactance of the inductor. And I've got to include it into the phase here, but the capacitor is still not there essentially in the circuit. So if I do that, I would just say the current is a function of time, which would be V maximum divided by the impedance, and in this case would be the square root of R squared plus XL squared. And then we would have cosine of omega t plus, and we're looking for this phi, so it would be the inverse tangent of XL minus XC over R. But of course, the XC I can cross out. That switch hasn't been opened yet. And then, of course, writing it the way they would want me to write it in terms of the frequency and the inductor, I would write the reactance of the inductor as omega and L. So this reactance of the inductor squared would be omega squared over L squared. And then this would be cosine omega t plus the inverse tangent of, and then I would write this as omega L over R. And of course, they don't give me any numbers, so I can't, plug anything in, but that should be what it is in symbols. In fact, let me jump to the solution. They got the omega L, they've got, well, they write it as a delta V. Yeah, good. So that's looking good. Going on to part D. Part D says after switch 2 is also opened, the current and voltage are in phase. Find the capacitance C. So remember they said the C wasn't known, but again, let me come back to our beginning discussion here. The phase is determined by the reactance or the difference in the reactance between the inductor and the capacitor. So they state very clearly that when you open this one, they are in phase. So this equals to 0. So that would mean tangent of 0 is equal to XL minus XC over R. And tangent of 0 is 0. And of course, if we multiply by R, that just gives us XL minus XC is equal to 0, or XL equals XC. So they're indirectly telling us that this frequency is the resonant frequency. This is the frequency where this kind of magic happens, where the impedance is the smallest, where these two are equal, and therefore the impedance is only equal to the R. And so even though the both switches have now been open, it's really kind of the same current as we got in A, as if there was only a resistor there, because those two have now been balancing each other off. And so to get to that frequency, I guess we would put in the equation for the reactance of an inductor and the reactance of a capacitor. And then, of course, solving it for its frequency, and I'll do angular frequency first, but omega squared would equal to 1 over LC, or omega would be 1 over the square root of LC. So that's the common answer I think we've seen throughout this chapter, that this is the either the natural frequency or the resonant frequency of this circuit. Of course, they asked for the capacitance, so let me not go down this road any further, but to put C to the other side, and so I get 1 over L and then omega C, and now I'm answering the questions in terms of the stuff given. They've given me an L and R, a maximum voltage, and an omega, so there's the L and there's the omega. So that must be the equation for the capacitor. Keep that in mind, because remember I said we wouldn't want any answers to have a C in it. So if I'm working along here in a little bit and I come across a C, I'll substitute this in, because we don't want our answers to have a C in it, because the C is one of the parameters that, even though it's in the diagram, they're trying to say you don't know that one. You know the L, the R, the omega, and the delta V max. Okay, so E is find the impedance of the circuit when both switches are open. Well, they kind of already gave that away, and I mentioned it. When both switches are open, they are saying that they were in phase, and when they said that, they're saying the reactance of the reactance of the inductor and the reactance of the capacitor are the same thing. So that goes away. So the impedance would just be the R. Yeah.
So it's the same as that previous one.
R. Mm-hmm. So it's the same as if the switches were closed. which of course that's why we call this a tuning circuit, because it, you know, there's a certain magical frequency right here that those two balance each other. They're like they're not even part of the circuit. And so high frequencies get blocked because of the inductor, and low frequencies get blocked because of the capacitor. But at a magical frequency, those two balance each other, and you get the smallest impedance you ever can. That's the current that's going to flow in this. So
Okay.
at a bunch of different frequencies, a good example would be an antenna. If I just put up an antenna, I get hundreds of different frequencies from all the TV and radio stations and all the Wi-Fi. I mean, I get all those frequencies, but the truth is I only want one, and, or a narrow range of one. And so maybe I'm trying to get channel 2 on my TV. You know, I would want to get this adjusted so that I get the most current for the frequencies at channel 2. So I'd have the correct value of an inductor and a capacitor such that they balance each other at that frequency. Channel 2 must be 50. The low side is 54, and they vary the frequency up to about 60. So from about 54 to 60 has all the coded information for channel 2. So I really only want the frequencies that are in that range of 54 megahertz to 60 megahertz to have current flowing in. Anyways, I probably said too much on E, but E is one of these questions that it's, if you kind of following what's going on, it's really easy. Well, it's just the resistance, because the reactance of the inductor and the capacitor canceled off. That was the whole point of the earlier comment about them being in phase. Okay, so F says, find the maximum energy stored in the capacitor. Now, we've got to go back a ways to the energy stored in a capacitor, but it was 1/2 CV squared. I guess that would be chapter 26. Now, if they're after the maximum, so I'll just put a little maximum underneath here, they must be then asking for also the maximum voltage on that capacitor. And now I'll do a little fancy substitution, starting with what I said earlier back here in part D, that if I ever see an equation that has a C in it, I'm going to put 1/L omega squared, because the tradition is to put the answer, well, to give you number, if the problem gives you numbers, the tradition is to put in the numbers and give you a number answer. But if the numbers are not actually given, then the tradition is to put in symbols that were given in the problem, and they made it very clear what was given, and they made it very clear C was not given. So I don't want to C in my final answer. So I'm going to use that in this step. Now, I need to be a little careful with maximum here, because this is actually the maximum on the capacitor. I don't want to confuse that with the maximum voltage generated by
the power source.
By the power source. So I hope my symbolism here of maximum didn't get confused. That's why I want to put a little cap underneath here. So this is where I would then apply, I guess I'll call it Ohm's law for AC. We know if you take the current times the resistance, now we have capacitors. Capacitors and inductors don't really have resistance. That's why we call it reactance. They do oppose the current, but they do it for a different reason. It's not a resistance that makes heat. It's actually an internal electric field. In the case of a capacitor, the internal electric field is because of the charges on the capacitor. Now, in the case of an inductor, the internal electric field is Faraday's law. The changing magnetic field produces an electric field that opposes the current. So that's a little harder to understand, the internal electric field of the inductors. I suppose that's why we did it just recently and late in the semester, because it was easier to understand capacitors and their internal fields. Anyways, so applying Ohm's law, which would be current times the reactance, and since we're looking for the maximum voltage on the capacitor, I would say I want the maximum voltage or maximum current in the capacitor, although they're in series. So it doesn't make any sense to talk about the maximum in the capacitor versus the maximum in the inductor versus the maximum in the resistor versus the maximum in the power supply. They're all
They'd all be the same.
Yeah. So I'm just going to put max. But that's nice because I did that a little earlier. And I guess I didn't explicitly redo it in E, but remember we said the impedance when they were, even when they were both open, is still R. And so we said that's going to give you the same thing that you got back in A. And so that maximum that we got in, the maximum current that we got in A is the maximum voltage from the power supply divided by the resistance. So right here, I'm going to put V of the power supply. In fact, maybe I'll use their same symbol, delta V, so that it doesn't get confused with the maximum on the capacitor. And then divided by the R. Oh, and I think I forgot a square right here. Yeah, see, this was maximum, so this should have been squared. So that'd make that one squared and that one squared. So that's the maximum current. And then, of course, this is the reactance of the capacitor. So this would be an omega squared and a C squared. Oh, back to another C here. So this is going to be 1/2 1 over L omega C delta V max over R squared 1 over omega squared. But now I've got this C squared, and as I said again, why don't we, write that as an L omega squared, and then that whole thing would be squared. So place of my C, in this case it's a 1 over C, so I'll take the reciprocal. All right. So it looks like I got a number of things that cancel, and it looks like right here, this downstairs is got 4 omegas, and so does this. So that's nice.
Yeah. In fact, just the LW squared, that would cross out with just one of the LW squareds.
Oh, okay. That
Yeah.
too. Yeah, that's a good way of looking at it. But as I read across here, I still have a 1/2. But it looks like that L downstairs, and with 2 of them upstairs, leaves me with just an L. And then a delta V max squared over an R squared. And so now I have it written as the way that I think they want it written. And that is no C's, and certainly no voltage maximum from the capacitor. Now, voltage maximum from the power source, that's okay, but maximum of the capacitor was not given, and likewise current was not given, and reactance was not given. So I had to substitute all those in here to get the form of the answer that would be what they're looking for. And then G says find the maximum energy stored in the inductor. I guess I have a couple ways of doing this. I'll start with the easy way. Actually, either one's really hard, but the easiest way is that the energy in the inductor just swapped back and forth with the capacitor at resonance. So I just did the capacitor. So I don't need to do it again. And that should be the answer for the inductor. Now that's a little bit of a too easy, but trust me on the test, that would be nice. Just, hey, move on. I got the answer. So I'm going to go and do it a little bit harder and just remind you that the energy stored in an inductor is 1/2 Li squared. It kind of looks like this term that we did for the energy stored in a capacitor. Of course, capacitor, the voltage determined its energy here. The
Quick question.
current, since the current makes the magnetic field.
Quick question.
Yeah.
For the last bit of F, where'd the second omega squared go in the numerator? Oh wait, no, I figured it out. I got it.
Good. Okay.
Sorry.
Good.
Okay.
Okay, and so like we did on F, maybe I'll put a little word under here, maximum, because again, they're asking for the maximum in the inductor. And so that means over here, they're after the maximum current. And that's what makes this problem actually a lot easier than F, because the maximum current is the maximum voltage from the power supply divided by the resistance. So I'll just square it. And
I do have actually one quick question on G.
yeah.
The symbols you got, the horizontal hashes at the top and the curve at the bottom, is that a U or a V?
Yeah, it's supposed to be U for energy.
All right. Whereas up top it was a V. Oh no! I see something.
Up here, yeah, that's an ugly looking U also. It's a U for energy.
Okay. I'm glad I asked that now. That would have been confusing later.
Yeah.
So let me fatten that one out. Okay. Yeah. I'm so used to seeing you use that little tail at the end, like a moo. So.
Oh, well, yeah,
but I get this. I get
that's
the
a
symbology.
lowercase U.
Even
that's
caps.
Supposed to be an uppercase U, and that's supposed to be a Greek letter mu.
Yeah.
And
I've always written my capital U's even just as a very large U with a large tail.
Okay.
Yeah.
That could be helpful because yeah, they are ugly, and that would help keep
similar.
it. Yeah.
Yeah.
Actually, I like that a lot. Yeah, I've always done that with my Z's and my 7s. A little dash isn't kind of standard, but it's it's standard in engineering writing because, boy, a Z can easily look like a 2.
Unless you do a cursive too.
Unless you're not real
careful. And then that starts
careful.
looking like an alpha.
So the dash really helps.
Okay.
And the 7 can look like a capital or like a 1 at a dash. So I've done that for years and years. And I've been getting in the habit of doing the Q's. I kind of got away from it. But the Q with the dash is real helpful also.
Okay.
Otherwise, it might look like a G or a 9. So anyway, so back to this problem. So G, I guess I'm done. Once I just put in the equation for the maximum current, which is voltage divided by resistance, I have the things that are given, the L, the maximum voltage and the resistance. And notice it does match what we said it should come out, which is the same energy we got for the capacitor. So this problem could have been a lot easier had they asked for the inductor first, and then you asked for the capacitor and you realize it was the same thing. It would have been just a couple of steps. But this was probably more educational in F to kind of go through the details. Let's see, what's this, page 3 here? All right, and then moving on to page 4. And where are we? G, Is that it? Oh,
H.
yeah, no, there's more to it. H,
Yeah, it goes all the way to I.
and then there's an I. Okay, yeah. So H is uh, now the frequency of the voltage of the source is doubled.
Mhm.
Okay, so for clarity, let me say that the frequency that I'm going to double, so 2 omega. So the frequency was omega. Now I'm going to double it. So I need a different symbol. And the one that comes to my mind first is to use like just a prime. I could use a subscript, but it's good with you. I'm just going to say omega prime. Okay. Because now they say that, you know, as it says now the frequency of the source is doubled. Find the phase difference between the current and the voltage. All right. So the phase is XL minus XC over R, where XL, the reactance, is the frequency times L. And of course, now we're at a new frequency. So we're at a frequency omega prime. And we are also the reactance of the capacitor. So I'll put an omega prime over C and divide that by R. And of course, then to get the phase that they ask for, I would be taking the inverse tangent of all that. Oh, no, that was good right there. Inverse tangent. And then here's where this new frequency, omega prime, is twice the original. So let me write this as 2 omega L and write this as 2 omega L. So my omega here represents the original frequency. And again, I think that's what I have to do because that's kind of the tradition. Give your answer in terms of the stuff that was originally given. And of course, if those are numbers, then put in those numbers. But if they're symbols, then you got to do that symbol. So I don't want my final answer to have an omega prime in it. I know that. But an L is good, an R is good. Oh, a C is not. So let me keep going. So this would be 2 omega L minus 1 over 2 omega. And in place of a C, coming way back here, I guess this was part D. Remember, C is this 1 over L omega squared. So I'll tell you what. Let me just write it as two factors because I've got this 1 over 2 omega, and then this would be 1 over C. And that 1 over C is what this is. This would be the L omega squared. Yeah. And then it looks like 1 omega on top and the omega on the bottom for that second term in the numerator would cancel off. And I have, this is good. I have like terms. This is just an omega L, and this is an omega L. This has 2, and this has minus 1/2. So 2 minus 1/2 is 1.5. Let me write that as 3/2 omega L. And so inverse tangent, and then I can simplify this compound fraction, 3 omega L over 2 R. And that was quite a few steps. Let me jump over to solution, make sure I did this right. Okay. I'm not sure I like the author's answer because he has this answer. He has inverse tangents of 3 over 2r times the square root of L over C. And that might actually be right, probably is, but I'm a little bothered because he's got a C in his answer.
So he's not replacing the C.
Yeah, which it's okay. I mean, it's kind of an unwritten rule that you shouldn't have C's in your answer. What did he do back with the capacitor? Let's see. Capacitor was F. Ah, good. So in F, he did it as I would have suspected. He took C and he wrote it in terms of the given stuff. But he didn't carry that through for H. But let me just check that we have the same thing here. So let me circle. So this is my answer. And he's got this one here. And I'm pretty sure we're talking about the same thing. Let me just put the L. And then jumping back to our answer to D, the 1 over C would be an L omega squared. And so it looks like inverse tangent of 3 over 2r. And then this right here would be an L squared and an omega squared. So you take the square root, you're at omega L. Yeah, and sure enough, that's the same thing. So it is the same thing. It just didn't
You just
match.
didn't write it the same way.
Yeah, and it also looks like my
Yeah, your video quit.
video stopped there. So, and seemed to be on a regular time basis. What am I doing different?
Hmm.
When I had this on before, it was because I had my screensaver on, but I fixed that. What if I did something different in Zoom? No, I don't think it's Zoom because it's, well, I don't know. Well, I'll try to figure it out, but not today. We'll just keep resetting here. Might have to do it one more time before the day's over.
Yeah. And
Okay.
then we have an I.
So yeah, so there's H, and then I. Let me come back to the question I. Find the frequency that makes, so again, a different frequency, but we want to write it in terms of the original frequency. But find the frequency that makes the inductive reactance half of the capacitance reactance. Okay, so we're looking for this. We're looking when XL is 1/2 of XC. Okay. So let's call this new frequency that we're looking for. Now, I don't want to call it omega, and I probably shouldn't do omega prime, because I just did that. How about omega double prime? Yay. All right. So the frequency I'm looking for is omega double prime. So this would be, the reactance of the inductor would be omega double prime times L, and then 1/2, and the reactance of the capacitor would be omega double prime L. No, sorry, C. So if I bring my frequencies together, omega double prime squared, I would get 1 over, and then there's a 2 and an L and a C. Now, if you kind of remember here, the original frequency was equal to 1 over the square root of LC. That's one thing we worked out in step I guess it was back in D here, where they told us they were in phase. the two were equal to each other, that is the reactance of the inductor and the reactance of the capacitor. So we got, let's see, that's the end of page 2. So yeah, it was right here, the start of page 3. We did this, and then I made this little comment that this was what omega would be related to. Or we could just substitute in what C is right here. That might be an easier way to think of the same thing. Maybe I will, I'll just do that. So we had done what C is, and so this would be an L over the omega squared, and then the L's would cancel off. And so if we take the square root, we get
I think that the video froze again.
the
Yeah, the video froze again.
crazy thing. All right. Okay, so what I was trying to say, I don't know where it froze, but remember this, 1 over C, we had C equals 1 over L omega C. So I can replace the C with L times omega squared, and then the L's cancel off. So then I just have the omega double prime squared equals omega squared over 2. And then the last step, when I take the square root, this would be the original omega and then the square root of 2. So that would be the new frequency that would give us this condition that the reactance of the inductor is only half that of the capacitor. So the capacitor is a little bit stronger, which makes sense. We know it would be a lower frequency. We know we're going to be dividing by something because we know we have to go, or something greater than 1. We know we have to go down in frequency so that the inductor dominates the, the capacitor dominates the inductor. But anyways, that's what it came out to be. Nice. Long one.
Yes, definitely.
Yeah. And by the way, that's one of the video solution one. If you wanted to scan that, I did things a little different than the video solution, so you kind of see it both ways. But somebody asked about that one this weekend, so I remember one evening making it, shooting it on out there.
I had skimmed through the emails that I'd gotten. I didn't see it, but may I just skipped over it? I'll check.
Yeah, I can send it to you again, or maybe, yeah, double check. I hope I didn't mess up and not send it.
No.
No, you sent it. Oh, at least to my class because I was the one who asked for it and I got it. So, and I know like Gina, she got it too because she was confused on some things.
Okay. I'll double check that, but usually what I do is I send it to the person who asked, and then I send it to everyone, and I've got a little group email.
Oh, there it is. I see it.
Okay.
All right, so I'll check it out there too.
And see if Gina
But
got
I
it.
appreciate having gone through it here because that helps.
Yeah, I thought going through it a second time, and or more importantly for you, live would be worth it.
Thank you for that.
Yeah.
Okay. All right, and then I'll look forward to 65 later.
All right. Oh, bummer! I forgot to write down what time this. I started the video. Huh.
You started like right at 3.
Yeah, right at 3.
I've been here.
This is the first one you did, so.
Okay.
Yeah.
Yeah, I know it was the first one, and so I wanted to. Anyway, so yeah, I'll just say like about 3. Okay, so this is 3:53 right now, and it looks like Jake's asking one. Could you please do an example of a motion EMF induced by a rotating rod in a magnetic field? Okay. Sure. And I think there's a good one on the homework. Maybe I'll pick it off of there so I don't make it up. I thought that, oh, there's a helicopter one. Okay, yeah, let's do the helicopter one. And it'll be a motion EMF. So that's got to be back in chapter 32. Let me find the homework. 32. No, 31. Yeah. Because, okay, 31. I think I'm in the wrong chapter here. Let's go 31. Let's see if I can scan it here. Yeah, it's number 27. Okay, so let me do a chapter 31, number 27. We'll call this page 1. And let me just swing back here to the chat. Jake, question for you. If I put that the EMF from a translating, not rotating, but translating rod is BLV, could I start there, or should I show you that that's what you get from just a translating rod?
I'm fine with that. That's kind of like the railgun stuff you were.
Yeah.
I think that's good. I think Don goes over
Okay.
in his review, but the rotating one I thought might throw in some extra twists, which I thought maybe.
Right. And it does a little bit, and that's why I wanted to know where to start. So if you'll let me start that we've already done a translating one, then the rotating one is to think about it this way. So if you've got this beam sticking out and rotating at some angular speed omega, here's where you can kind of take advantage of maybe some calculus and say, well, let's look at a really small piece of it. And so I will say, let's take a small length. I would be tempted to call it DL, but it's also radially outward, so why don't I also call it DR? But I'll start with DL because this is where I was saying, if you were to take this whole rod and, of course, think of it spinning, one little section, and in the limit as it gets smaller, it's just translating it. So you could change this equation for a translating one and say a little bit of voltage equals to the magnetic field at this point times a little bit of length. And so I'm going to replace the L with the DL times the velocity. And that would be the little bit of voltage that was created from, say, the left side A to the right side B. And so if you think about a bunch of these, another one, 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 and 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 you say, what is the total EMF from beginning to end? Then you might write it in terms of this. Let's add up all the little EMFs from each of those little pieces. And that would give us the total EMF for a rotating one. And so this would be the integral of B dLV. And you might even then want to write the DL as a DR, since moving outward is definitely the length of the rod, but in kind of a polar coordinate system, we usually call this an R. So it might look a little better here if you called it a DR. And it would definitely look better if you then replaced the velocity of these. Now we really have to go way back. We got to go back to Physics 121, Chapter 10, and say that the translating speed is the angular speed times the R. And so if you go from here to the full length of the rod, so from R equals 0 to the full length, and I'll just call the full length of it L, then you would get something like this. The B can be pulled out if this is spinning in a uniform magnetic field. And that helicopter problem is a uniform. I haven't read it yet, but I'm going to read it here in a second. And then the omega is a constant, as the whole thing has the same angular speed. And so you just have an integral of R, whoops, no square yet, we got to integrate it. Integral of R dr evaluated from 0 to L. So this becomes B omega, and then it becomes R squared over 2 evaluated from 0 to L. And so then you get B omega L squared over 2. And that then would be the formula for the EMF of a rod that's spinning. And now I'll go back to the question. The helicopter one was number 27. It says this, a helicopter has a blade of length 3 meters. So in our problem, L is going to be my 3 meters. Extended out from a central hub, and it is rotating. And so they have an omega, although they list it in 2 revolutions per second. And our standard units are radians per second. So each revolution is worth 2 radians. So when I put in my numbers here, I need to put in my units as in radians per second. So I'll take the 2 revolutions per second and change it to, I can do this as 4 pi radians per second. So there's the spinning propeller. And then it says if the vertical component of the Earth's magnetic field, so this is where this derivation was derived with the magnetic field going downward and or upward, but perpendicular to the movement of it. And that's would be perfect, because that's why they say the vertical component at that particular location is 50 micro Teslas. And then what is the EMF? So then it's just a matter of plugging these into the calculator. The B is the 50 times 10 to the minus 6. The omega is the 4 pi. The L is the 3 squared. And then that whole thing divided by 2 makes a small amount of voltage. But nonetheless, a voltage. And so, yeah, there's your motion EMF from a rotating rod. In fact, I don't know if you ever heard the phrase St. Elmo's fire, but the St. Elmo's fire was during heavy winds and electrical storms, the tip of a mask can actually get so much charge build up on it that sparks fly off. Now that's more of charging by rubbing than it is induced EMF, but helicopter blades can do the same thing. They're usually not enough that you can actually see them, so they're not like the dark skies of the old sailor days and the electrical storms. You can't see them without your night vision goggles, but in military operations, can be a big problem. You can see the helicopter and you can see the sparks flying off the tip of the helicopter blade.
That's interesting. Thank you.
Yeah. But I think most of the voltage comes from the rubbing, like we did way back at the beginning, the transfer by charge than the spinning in a magnetic field. I definitely can see it with some light amplifying materials. So your night vision goggles.
So it's just rubbing with the air molecules, which is causing electrons to bounce up, or
Yeah, and they can build up. I don't know. Have you ever had this experience where you get out of your car and you go to shut the door and it shocks you? You know, there's a spark.
no, I don't think I have.
And that's happens. I don't know about real often, but pretty common. And that is the rubbing. That's the rubbing of the car against the air. They try to make car tires so that doesn't happen. It's really kind of annoying. I haven't, personally, now I think about it, I haven't experienced it in a long time. I used to have an old Toyota that did that to me all the time. And so I think there was some combination of it rubbing and the material that was on the clear coat of the paint, plus the tires wouldn't let it discharge. But anyways, it never would discharge, and every time I'd get out to close the door, it would just zap me. It would just drive me crazy. Like, ow, that one hurt. All right, well, I better move along here. Let's see, I think Daniel, you were next. Okay. And number 34, or chapter 34, number 15. And the time is 4:06. Good. I'll write that down. All right, so chapter 34, number 15, page 1. So let me find that homework assignment. That's the one that I send a separate PDF. Yeah, here it is. All right, so number 15. Good. And this is energy carried by the electromagnetic waves. All right, so 15 says, how much electromagnetic energy per cubic meter is contained in sunlight if the intensity of the sunlight at the Earth's surface is roughly 1,000 watts per square meter. Now, I'll do a little bit of review from the lecture here, but one thing that I hope you started to get out of the lecture, and the whole reason we called this chapter the electromagnetic waves, it's kind of hard to draw. In 3 dimensions, but I'm trying to draw upward on the vertical axis an electric field, and coming out of the page on a z-axis a magnetic field as the wave traveled along the x-axis. So what I hope you got in this last week's lecture was that these electromagnetic waves are made out of both electric fields and magnetic fields. And there is some nice connection between the two. One of the connections is that the electric field and the magnetic field are at right angles to each other. And they're even together, those make a plane that is perpendicular to the direction they travel. So we've got kind of all three dimensions going on. They travel in the x direction, the electric field is in the y direction, and the magnetic field is in the z direction. So another neat pattern was that the electric and magnetic field are mathematically related to each other. One makes the other. And so the changing electric field makes the magnetic, and the magnetic, which is changing, now makes an electric. So mathematically, if you know one, you also know the other. The part that is important for this problem is the energy. And I'll try to make this as a U sub E and a U sub B, because the energy density, which we touched on way back in chapter 26, but didn't really do much with it. In fact, I even made a comment back in chapter 26. I said, don't forget that the energy density, and so the energy inside of that capacitor, is related to its electric field according to this equation. 1/2 times the permeability of free space times the electric field squared. And we recently, working with the inductor, saw the same thing, that it would be the magnetic field squared, and also has a 2. It's just that the mu naught is downstairs instead of the epsilon naught upstairs. And so those are the energy densities. And so for electromagnetic waves, if you wanted to find the total energy density, you would have to remember that the wave is made up out of both electric and magnetic fields. So it's part electric and part magnetic. And in fact, I'll prove it to you, but they're equal in their magnitude. And that's what we're after here in this problem. It says how much electromagnetic energy per cubic meter. So that's it, the energy per cubic meter. So it's a combination of these two together. How much energy is in the electric field added with how much energy is in the magnetic field. So in the electric field, I would write this 1/2 epsilon naught E squared. And then for the magnetic field, I would add to it the magnetic field squared over this 2 mu naught. Okay. So again, this is my calculation for the energy density. Now, I don't really need to go through and calculate all this, although I will, because I said I would and I'd get started. So I'm going to go ahead and begin. But one of the questions here is, well, what electric field do you use? Because the electric field is changing. Right, and that's where, if you're talking about then the average, you would then use the RMS. And the same thing about the magnetic field. So I'm going to borrow the concept of RMS from our circuits, which was chapter 33, and say, look, this would not be the maximum, it would not be the average, it would be the RMS. Now, again, maybe unnecessarily, because you're going to see I'm kind of doing this the long way, but this is another way of saying this is that, and I'll show you, these terms are actually the same amount because I'll write this as 2 over mu naught. And so remember this relationship that if you know the magnetic field, you also know the electric field. So this would be the RMS of the electric field divided by the speed of light. And then the speed of light squared would be this mu naught over epsilon naught.
The left term, is that that E RMS still squared?
Oh, yes, it is. Thanks.
Okay.
Yeah. And then, of course, the mu's cancel off. And so this is the 1/2 epsilon naught E squared. And this was my way of really making this problem harder. And I didn't mean to make it harder so much as to show you that this term, which is the energy in the magnetic field, is actually equal to this one, which is the electric. And so the electric and the magnetic have the same amount of energy in it. So if you add 1/2 plus 1/2, you just get 1. And your book decided to write this not in terms of the RMS electric field, but in terms of the maximum. And so as you, again, borrow from our circuits, if you take the maximum and you divide it by the square root of 2, you get the RMS. So this boils down to this equation. Okay. And that is the energy density in terms of electric field. And that's what I wanted to show you, but it's not even really necessary for this problem, because this problem does the following. It says that if this is the energy density, let me just write it in terms of units, okay? So energy per volume, which we could write as energy per area times length. And then if we were to multiply this by length over time. So in other words, if I took energy density, mu, and multiplied it by length times time, that's speed, I would get, and watch what happens when the lengths cancel off, energy per time, that's power, per area, that's intensity. And now in retrospect, I kind of wish I hadn't done all this, because I think I might have redirected you too far away from the problem. But this is really more important for, I guess, the next couple of problems. But this is how you would answer this question, because they gave you the intensity. So I would answer this one by simply saying the energy density is equal to the intensity divided by the speed. The intensity is 1,000 watts per square meter, and the speed is 3 times 10 to the 8th meters per second. And checking the units here, remember a watt is a joule per second. The meter squared from here. Another meter with a second there gives you the joules per cubic meter. So really this problem is much shorter than I made it out to be. I was, again, just thinking I could add a little bit more to it. All you need to do is take the intensity as 1,000 and divide it by the speed of the electromagnetic wave, and that's your energy density.
So the intensity is the I, and then the electromagnetic energy per cubic meter is the U?
Yeah.
Okay. Yeah, I've done I have like 3 more problems and then I'm done with all the homework. And when the problem started switching from I as current to I as intensity. It kind
Intensity.
of threw me for a loop a little bit.
Yeah,
'cause
yeah.
it's different I for everything still.
Good
Mhm.
point. Yeah, we got I for current, we got I for intensity.
Yeah.
Some books then, because of that, like to use the lowercase I for current. And then reserve the capital I for intensity.
Yeah, but then that makes me think of I hat.
Well, it's got two problems, I think. Yes, it can get confused with the I hat, which is the unit vector, but it can also get confused with the square root of -1, which is the I. And we haven't really done any mathematics with the square root of -1, but they're very convenient when you're doing AC circuits. We just touched on AC circuits one chapter and did a little bit with the series, inductors, capacitors, and resistance, but that's going to get very confusing. In fact, I don't think anybody here is in our circuits class, but the circuits class, this is what they do. They start the class using lowercase I for the current. I'm not sure they use intensity much because they're not doing electromagnetic waves, but that's kind of the logic of why. You can save the capital I for intensity. Then when they get to AC circuits, after they learn about DC circuits, they start doing the square root of -1, and that I could get confused with that I, so they actually change the math symbol of the I to the J. And so electrical engineers like to use J for the square root of -1, so that they have the I for the current. And it's kind of a common practice in electrical engineering. So do our best to keep our symbols straight, but they nonetheless, just
It's
so
kind of
many of
like
them.
that thing you mentioned at the beginning of the year where when you were in school, you had a Russian professor and then
That was crazy. Yeah. Right. And that was his thinking. His thinking was there's so many symbols. I'll help out the students by using the Russian alphabet. But I had never seen the Russian alphabet, so that was crazy symbols to me too. Which is why, as you said, I tried to convert all his symbols to Greek, and then I ran into troubles when he got all the way through the Russian alphabet and started using the Greek alphabet as well as the Latin alphabet. Yeah.
Needed more alphabets.
well,
Yeah, maybe we got to switch over to the Chinese alphabet. Okay, so who was asking that one? That was Daniel. All right, and he got it and he took off. All right, fair enough here. All right, so let's go to the next one here. Zach, just looking at the solution manuals, I noticed that some of the problem numbers have an asterisk next to them. Oh, what does this significant? There is a book you can buy that has them worked out. And so, but not all of them. And so they put an asterisk by the ones that are worked out in the student solution manual. So
Okay. So
wait,
we can basically ignore that.
solution manual.
Right.
Let me look. I hope I'm not telling you wrong. I'm pretty sure that's what it means. What I publish for you guys, what you guys look at, is the instructor solution manual. I get these solutions to all of them.
Right.
But there is what they call the student solution manual, and the point is that the students, to help them learn, should have the solutions to some of them, but not necessarily all of them. unless the instructor wants to give it to them. The instructor can, because the instructor has a solution manual.
Mhm.
But they usually start the thinking. The publishers start the thinking by saying that, you know, we will give you, the instructor, a solution manual that has all of them if you want to look at them, which isn't bad. I mean, I do like looking at the solution, but I personally like to do them myself first and then look at the solution manual, because well, sometimes it could just be good. It's done different, you know.
Right.
Anyways, but it's also good for, you know, the solutions to be known to, you know, the student can buy a solution manual that has some of them, but not all of them. That's just the thinking. So I'm pretty sure that's it.
Okay.
I'm pretty sure this is explained if you're really curious. There's also a color code to them. Now, when Don copied these, they were just copied
Black and white.
black and white, but the problems are black and blue and magenta, and those are listed from easy to medium to hard. And I think you see that best in this last solution that I gave you, because I just copied straight from the PDF. And so all the coloring is still there.
Yeah, so we can see which ones are.
You can see which ones are black and which ones are blue, and I don't have any magenta ones.
Okay.
But, anyways, I'm pretty sure this is all, the color codes are all explained way at the beginning of the textbook. If you went before the table of contents, and it says things like, well, that's where it says things like, hey, we'll make electric fields in, they give the color, it's kind of a burnt orange, and we'll make magnetic fields in green, and keep that in mind. That might help you when you're learning, you know.
Okay.
So I tried to keep to that. I know that when I'm in class, I try to have my green pen and my orange pen already, and that's why I went out and got the green pen and the orange pen, and try to still stick to that. But and I think current is in purple, but it can be helpful.
Okay.
Yeah. All right. Oh, and let me come back to the Zoom here. Yeah, I think that was a last question there. All right.
Looks like it.
I'm curious, besides the practice tests you provided and redoing homework, is there anything else you suggest looking over to help prepare for the exam?
The best thing is practice problems, definitely. No, and it probably doesn't really matter where you get them. The practice tests are good ones, because I think it makes you kind of get a feel for, you know, what it's going to look like. I think by this time in the semester, you know, it's just going to hopefully be just like the homework problems. So, yeah, I would suggest, if you've done all the homework and you've done all the practice ones, then also go to the, you know, end of the chapter and just pick some other ones.
Okay.
Yeah, just now, and I guess I would encourage you to maybe focus on blue ones, because the magenta ones tend to be a little too hard for a test, but hey, give them a try. I guess I'd say this: if you do the magenta ones, don't pressure yourself into the 25 minutes.
Okay.
But the blue ones, I would see if you can get the blue ones done in 25 minutes. Yeah.
Is that out of the OpenStacks or?
Oh, and that's out of the survey one.
Okay.
Yeah, the OpenStacks has some good problems too, but I don't think they're color coded, so I can't say much about those. But they're still good problems.
Okay, cool.
If you're still looking for more problems, yeah, do the ones in the OpenStacks. But in the survey one, the black ones are fine too, but know that the black ones you should do really quick, and the blue ones you should do under 25 minutes, and the magenta ones you should just be able to do them, but not necessarily in 25 minutes.
Okay, and those are all in the PDF?
Yeah, and then yeah, the textbook you should have in PDF, right? From the very first email I sent.
Yeah, I think I downloaded it. I
Okay.
haven't looked at it in a while.
Yeah. Well, yeah, and you can decide. I don't know. Like I said, really wouldn't matter which textbook you look at, but
Okay, cool. Thank you so much. I think I'm gonna head out. I really appreciate your help today.
okay, good,
Yeah.
good.
Same thing, Mike. Thank you very
All
much.
right.
And look forward to 65.
Okay.
right.
Oh yeah. Let me write that down. Do
3365.
do 3365. Yeah. Okay.
All right. Thanks, Mike.
All right. Take care.
Hi, Dr. Young.
Hey, Daniel.
So I just had a quick question. Like, would the best way to study just be doing the practice test, or and then like random homework problems and stuff?
Absolutely.
Okay.
I think just doing some problems, and obviously the homework first, and then obviously those practice tests. Those are the first place, especially since you've got the solutions worked out. But then I would encourage you to go and look at the back of the book. Just go to page, chapter 33, and try a bunch of those. And then if you look in the PDF, they're color coded. So I would say the black ones you should do fairly quickly. Those are supposed to be the easy ones. The blue ones are more of a test level. So you should be able to do those in about 25 minutes. The magenta one are great practice, but if it takes you longer than 25 minutes, don't consider that a bad thing. Just, okay, as long as I did it, no matter how long it takes, I'm okay.
Okay. So this test is kind of more revolved around chapter 33, you said? Because you said go, like I would go to chapter 33 and
Sorry, I didn't mean to imply that. I mean that was just one of the 4 chapters. So go to 33,
okay.
try a couple of blue ones. Go to 32, try a couple of blue ones. Go to 31, try a couple of blue ones. Go to 34. Don't try anything too hard in 34. We didn't do a full justice on that one. And certainly
Okay.
don't do anything with momentum.
And then so like you said you would try and get this test graded really fast so you can tell if we need to take so we can tell if we need to take the final or
Right.
what?
Right. Yeah. So I'm going to do my best to get it to you. I know it. Let's see, guys. You take it on Thursday. I'm not sure what will happen Friday with Zoom. How many people will be here and how much grading I will do.
Mm-hmm.
I can see it going either way, so I better not plan on getting much graded on Friday. So, and usually takes me about 2 days. So maybe Saturday, Sunday, I'll be done. I know that's not too early, but at least to give you some idea.
Okay. Is there any chance you could send me the formulas to calculate the scores for both situations?
Yeah, but let me give you the short answer. It was on the email I just sent out for week 15.
Yeah.
So, okay.
I'm just like, I just don't know how to calculate my score if, say, I decided not to take the final, how that 25% changes to 33% for the homework and labs.
Oh, right. Okay. So, so let me say this way that, in fact, let me check the email. Here's the best way for you to think about it. If you, and I think you are, if you're gonna do all the homeworks and labs. So
Yeah,
okay.
I've turned in all the labs and I'm 3 problems away from all the homework.
Okay. All right, so count that as a given. Then take and average your tests. Now, right now, you have 2 tests. You know those scores.
Mm-hmm.
And then you can start playing with some numbers here you want. Like, let's say you just go, well, let's say I get 70% on test number 3. All right. If that average, okay, and if I'm looking at the email, the part that says without taking the final, if your average on the 3 tests are between 85 and 100, you'll get an A.
Okay.
If your average on those 3 is between a 70 and an 85, you'll get a B.
Okay. So basically, just play around with the third test score a little bit,
And
and see. So if it's, as long as it's above 70% average, it should be in a B.
yeah. Mm-hmm.
And same thing with, as long as